This is section 15.6 on tangent planes and linear approximation. This is exciting because this week gets the payoffs of all of the rest of chapter 15. I love the ends of chapters. I don't know, we get to actually use the stuff for what it's used for. So let's jump into it. In section 15.5, we learned that if you have a surface, which is a function of two variables, which is like what I've got up here, the input is a point in the plane, the output is a number. Then the gradient vector, del f, is this vector that has the two partial derivatives in it. These gradient vectors are orthogonal to the level curves. It feels a little weird. I think I kind of want to say orthogonal when it's two vectors. Like two vectors should be orthogonal to each other. If it's a vector that's perpendicular to something that's not a vector, I'm instead going to say that it's normal. I'm not sure if there's an official ruling on that. It's more of like a dialect grammar thing, but I'm pretty sure I should be saying that things are normal when they're not both vectors. Anyway, the gradient vector is normal to the level curves. So if you're looking at a contour map and you want to know how to get uphill as fast as possible, you don't walk along the level curves. That'll keep you at the same altitude. Instead, walk normal to the level curves. Okay, then we figured out that if you have a function of three variables, we get another data type indicated up here. Say the function of three variables is f of x, y, z. Then the gradient vectors of this, which look like fx, fy, fz, these are normal to the level surfaces. Okay, that's a little bit harder to understand, but the example I used in the previous section was imagine isotherms in space. Isotherms are, you take all of the, iso means same, therm means temperature, so same temperatures. Isotherms would be the surfaces that connect all the points in your room that have the same temperature. So like between me and the light bulb that's over that way, it's not all the same temperature everywhere along there, so those wouldn't be connected by an isotherm. But there would be probably be an isotherm some distance away from me, and then another one a little bit more distance away from me. Those are the level surfaces of a temperature function. Okay, now here's the main algebra trick that we're going to use in this section. It's the idea that you can switch between a function of two variables that defines a surface and switch it around to something called an implicitly defined surface, where we think of it as a function of three variables. So say you have a function of two variables, f of xy, and you're thinking of f of xy as the heights of a surface. So you're thinking of it as z equals f of xy. If you have this equation, you can think of it as a function of three variables by just subtracting the z to the other side. So here's a function. It's a function of three variables. If you plug in an x, a y, and a z, you'll get a number. The surface that we are interested in from our z equals f of xy is the one where this equals 0. This equals 0 is a level surface. It's the level surface at, I can't say height, at value 0. Of this function of three variables. So this function, you can plug in x, y, and z, and you get out a number. All of the points in space that give you 0 as the output is a level surface of this function. But that's also the same surface as the function we started with, a function of two variables. So this allows you to switch back and forth between a surface as a function of two variables and a surface as a level surface of a function of three variables. Why would we want to do that? That sounds complicated. Well, the nice fact about level surfaces is we know exactly what is normal to the level surface at every point. It's the gradient of this. So this is normal to del w. Del w is going to be, well, you take the x partial derivative of w, the y partial derivative of w, and the z partial derivative of w, and drop them all in a vector. If you take the z partial derivative of this function, you always get minus 1. So there's no z's in this first part. But when you take the x and y partial derivatives of this function, the z part doesn't come into play, and you're just working with x. So you get fx, fy, minus 1. So this is the gradient of this new function of 3 variables that we introduced. So what? Well, that means if you have a surface that's a function of 2 variables, by doing this switch around to a function of 3 variables, we find a vector that's normal to our original surface. So that means we can get a tangent plane to any surface, z equals f of xy. Just use this normal vector. Fx, fy, minus 1. And the reason there's a minus 1 is just because we started with z equals f of xy, and when we moved the z over to the other side, the partial derivative with respect to that z was minus 1. So that means that we can, whenever you have an explicitly defined surface, meaning a surface that's given by a function z equals f of xy, its tangent plane at the point at a point x0, y0, z0 just uses this normal vector. So you get fx times x minus x0 plus fy times y minus y0 minus, because I'm going to have minus 1, z minus z0 all equals 0. So any surface, you want a tangent plane to it. You don't have to do all of this like maneuvering between data types. It's all been done in advance. That's why this is in this blue box. To find a tangent plane to a surface, you use this formula. Take the x partial, the y partial, and there's no z partial to do, but you treat it as minus 1 because of this argument. Yeah. Just a quick note about the data types here. This fx is a number, and x minus x0 is also a number. So this is not a dot product. This is an actual multiplication of 2 scalars, 2 numbers. On to the next page. Okay, if instead you have your surface implicitly defined, that means that instead of having z equals f of xy, instead you have a big function that's a function of 3 variables, and that all equals 0, then you still use the gradient to get the normal vector, but now it's the gradient is fx, fy, and fz. So we'll use fx, x minus x0, plus fy, y minus y0, plus fz, z minus z0, all equals 0. So yeah, it depends how your surface is given. If your surface is z equals a function of 2 variables, you use the first form. If your function is, or if your surface is function of 3 variables equals 0, then you use this form. So let's see a couple of examples. We've got this surface z equals 4 minus y squared minus x squared. That's going to be a paraboloid that's like upside down. Oh, there's a nice picture of it here. I didn't even notice. And I want a tangent, I want the tangent plane to this surface at this point. Okay, well, all you do is you say, well, how is my surface presented to me? Is it z equals a function of 2 variables? Or is it function of 3 variables equals 0? Or if it's neither, like, which one can I turn it into the easiest? This one is z equals f of xy, with f of xy is 4 minus y squared minus x squared. The most common mistake I see students make when they're working on these problems is they start referring to f like a function, even when there's no f in the question. And that used to be kind of like acceptable and people let it slide in Calc 1 and Calc 2 and definitely in algebra, because we know that you mean like, oh, this is the function, this must be what you're talking about. But because there's two different approaches here, where one you think of it as a function of one variable, or one you think of it as a function of two variables, x, y. The other way you think of it as a function of three variables, x, y, z. You really need to tell me what f is before you start working with it. So this part here, like where if you're about to call f by name, you should say what you mean by f. Okay, anyway, we're in a function of two variables. So the normal vector to the surface is fx, fy minus 1, which we can take these partial derivatives. I get minus 2x, minus 2y, minus 1. And at this point, 1, 1/2, 11/4, I get a specific vector. Minus 2, minus 1, minus 1. So this is a normal vector to the surface. So you've got this paraboloid, and this vector is pointing like in. I think it's pointing in. Yeah, it's pointing inward, normal to the surface. Okay, you can use this normal vector both to make, ooh, I don't like this, both to make an equation of the tangent plane and to make an equation of a normal line. So we want a plane that just touches the surface, and then we want a line that sneaks out from the surface, that's normal to the surface. They're both easy to do. So here's the tangent plane. This is the same way we made planes for all of chapter 13. You take its normal vector, get x minus x0, y minus y0, and z minus z0. Here are x0, y0, z0 are the space point. Normally, I would recommend that you don't simplify very much, but here it's going to go pretty well if we simplify. So I'll just distribute these because it's going to make the answer look a lot better. In total, how many fourths do I have here? Here I have 8/4 and 2/4. That's 10/4. And here's another 11/4. So I've got 21/4 over here. And if I get the x, y, and z all on their own side, then everything will actually be positive. So it'll be possible to look at this plane without hurting our eyes. So this is a nice final answer. To be clear, the answer up here, where it was in the original standard form, is also totally fine. You might notice that they have different normal vectors. We have minus 2, minus 1, minus 1 as the normal vector for my initial answer, and 2, 1, 1 for the normal vector in my final answer. Those are opposite of each other, and that's fine. They point in opposite directions. They're both normal to the surface. Then to get a normal line, well, an equation of a set of parametric equations for a line is not too bad. You'll say x, y, and z equal start at the base point and head in the direction given by that vector. Every second we'll have the x go down by 2, the y go down by 1, and the z go down by 1. So this is a set of parametric equations for the normal line. This is pretty typical of how the gradient gets used. It kind of like is the core idea that makes the formula work, and then you end up with a formula that looks kind of gradient-like, but you never actually like use the gradient directly. Still, when you have this fx, fy inside of a vector, you should be like, oh, that looks like the gradient. Here's the gradient of f in here. But then there's this minus 1, and there was a reason for that. You can look back and see it. Okay, here we have a sphere of radius 5. Let's find the gradient vector at this point. Oh, it told us to find the gradient? Well, okay. So this is a surface, and we have two ways to find normal and tangent objects to these surfaces. You either think of them as z equals f of xy, which tells you that there's a normal vector that is fx, fy minus 1, or you get the whole thing to be a function of three variables, and it all equals 0, in which case the normal vector is fx, fy, fz. In every case, so like in the first one, it was easier to think of it as a function of two variables, so we just went with it and used the first option. You could do that every time. So like you could solve this for z if you wanted to, and I just really don't recommend it. You should avoid that. You get two ways to do things. Look at the two ways and see which one is easier. It's going to be a lot easier to just get it equal to 0. So I have x squared plus y squared plus z squared minus 25 equals 0. So I'll let my function be that thing, x squared plus y squared plus z squared minus 25. When I'm in that situation, the normal vector, well, a normal vector, is just do the partial derivatives. And in this case, where we're looking at a sphere of radius 5, and we're over at the point where we're as far in the y direction as we can go, so we're like at the edge of the sphere in the y direction, I expect the normal vectors to be pointing in the y direction. I don't know, let's see how it works out. So fx is 2x, fy is 2y, and fz is 2z. And at this point, 0, 5, 0, I get the normal vector 0, 10, 0. Said 0, wrote 10. 0, 10, 0. So in fact, the normal vector points in the y direction, which is what I was expecting. It's like if you have a sphere and you're looking over at the point that's as far as possible in the y direction, the normal to the sphere would point out in that y direction. If you want to be normal to the sphere, you go straight out from the center. So here I'm headed in that direction. Nice. Okay, next up is one more way that we use the gradient. Linear approximation is the idea that any surface, if you zoom in close enough, is a flat surface. Well, not like exactly a flat surface, but like approximately a flat surface. You used this in Calc 1 when you had a function. And the idea of linear approximation when you had a function of one variable was to zoom in on a point and say, well, close to that point, the function is basically a straight line, so I'll just use the tangent line to approximate what's going on there. Here we'll have the exact same plan, except instead we have a surface, and we'll say close to a base point, the surface is essentially the same as its tangent plane. That only works if the derivatives exist, but if the derivatives exist, then we're good. So let's see how it works. So how do we use the tangent plane at the point 3 minus 4 to approximate this? Well, first we would find the tangent plane. As usual, we have two ways to go. We can either try to think of the surface as z equals f of xy, or we can get everything all as a function of xyz equals 0. Here the f of xy is given to us. So we'll use the first plan. So here's a normal vector. A normal vector that we'll use is fx, fy minus 1. We'll have to take some derivatives, but that's okay. So the x partial derivative of this square root function is going to be, well, 1/2 times this thing to the minus 1/2. Times the derivative of the inside, which here is 2x. And then when we take the y partial derivative, we'll get the same thing. And then here's minus 1. These 2's cancel. So we get a relatively nice normal vector. And we actually have a point, 3 minus 4. I'll call this normal vector n and plug in 3 minus 4. So I'll get 3 over, what is this, square root of 9 plus 16. So I get 3/5 minus 4/5 minus 1. So this tells me that whatever this object is, which I don't know, I know what it is, but whatever this object is, like you don't need to know the shape, that's the point. Whatever this object is, near the point 3 minus 4, the surface acts like a plane that's oriented using this normal vector, 3/5 minus 4/5 minus 1. So what is it approximately? So the tangent plane, this is going to be our replacement for the real actual surface, is 3/5 x minus x0 minus 4/5 y minus y0 minus 1 z minus z0. And z0 looks like it came out to 5 here. All equals 0. So this is my tangent plane. I am replacing my surface, which is going to be all curved and not a totally flat plane probably, with this plane near 3 minus 4. Because this point is near 3 minus 4, I can drop this into my tangent plane and I'll get an approximation. So my x that I actually care about is 3.06. My y that I care about is minus 3.92. But like, I don't want to plug x and y into this crazy function. I'll just use this linear approximation instead to find z. And it's not exactly true, but it's approximately true. So let's do it. I need 3/5 of 0.06. 3/5 of 0.06. I think it's 0.036. Does that seem right? 1/5 of 0.06 would be 0.012. Because 1/5 of 6 is 1.2. Yeah, okay, so 3/5 of 0.06 is 0.036. Here I have 4/5 of 0.08. I guess I can give in calculator. Oh well. Four-fifths of 0.08 is 0.064. And then I've got minus z plus 5 equals 0. So I can get an approximation for z here. The thing you should notice is that z is approximately 5, but it's off by some small amount that depended on these partial derivatives. The formula we will write at the end here will simplify all of this process so you don't have to do it every time, but it just uses this idea. It says, replace the function with its tangent plane. It's close to correct near the base point. And then the little differences caused by being a little bit away from the base point will cause the output value to be like not quite 5, not quite the original value. They'll be off by this amount. Let's just get it right. 5 plus 0.036 minus 0.064. So I get 4.972. Okay, now does f of 3, does this equal 4.972? No. Instead, the final answer is that this actual function value is approximately 4.972. This is valuable when your function is complicated or when your function doesn't have a formula, but you know its slopes, you know its partial derivatives, and that's more likely in the real world. is that you'll have data that will tell you how fast things are changing. You won't have a formula for the function to plug it in. So you'll use a base point and how fast things are changing to get an approximation for the end result here. Okay, let's see the final formula. So let's say you have a function that's differentiable at your base point. We need the derivatives to exist, or this whole idea of zooming in and seeing a flat plane doesn't work. Like if there's a cusp or something, you don't zoom in and see a flat surface. So suppose the partial derivatives exist, then the linear approximation is the tangent plane, which is given by this equation. So we basically just like what are we doing here? We're going to solve for z? Yes, we're doing this, but solving for z. Weird. Okay, so you move the z minus z0 over to the other side and put the z0 back on the left side. So we'll have, let's call it L for the linear approximation, and you're going to have the z0 here. And then the rest of this is what we saw above, which was the x partial derivative times x minus x0 and the y partial derivative times y minus y0. I don't like this AB stuff. It's like kind of baby language. Like the base point is x0, y0. And then this should be x0, y0, and f of b is wrong. Yeah, okay, so just change this if you have this printed out. It's if the function's differentiable at x naught, y naught, then the linear approximation at the point x naught, y naught, z naught is the tangent plane, which is given like this. Fx times, fx at the base point times x minus x naught plus fy at the base point. This hasn't gone very well. Let's start earlier. The problem is the x partial derivative is its own function, but no, I want a number here. I want the, like this 3/5. I want the x partial derivative at the base point. And all this is times x minus x naught. And then I want the y partial derivative at the base point times y minus y naught. And then I would have minus z naught, but I'll move the z over to the other side and say this is our linear approximation. In the other case where you've got the surface defined implicitly, it's a function of 3 variables, then you'll get a different formula, and I'm not gonna... Can I make it look similar? I guess I'll say fx, at least the ABC and the f of ABC are correct here. I'll use the ABC notation here. That means this is A. The point is, if you have an explicitly defined surface, you do the partial derivatives of x and y, and you treat z kind of like specially. If x, y, and z are all in there, none of them is special, then you treat them all the same. So here, in this case, when we get to the z's, you just do the same thing. And then we still need, except I called it. It's important to get these right because you can refer back to these without using the argument up above. But at the end, we still need the final, the base output here. In this notation, the base output is not C. The base output is this this f of ABC. I've made this seem so complicated. The point of this is to simplify the process of building the tangent plane, so you just have a formula that builds the tangent plane instantly. And the point is that the tangent plane, to get the normal vector for the tangent plane, you just drop in the normal vectors that we got in the previous section. In one case, it's fx fy minus 1, which makes the approximation look like this. In the other case, it's fx fy fz, which makes the approximation look like this. Okay, so the last thing is, what's the short way to write this? Like, because this was not doing it really. So the way that we talk about small changes is to think about differentials. So in Calculus 1 or Calculus 2, when you had a function of one variable, you would say, well, close in here at a point, you would say, well, if the function is headed in this direction, we say that it goes up by dy when it goes over by dx. And that's why the slope of this graph is called dy dx. And then if you want to know how much y changes, then you say, well, one way to do that is to just use what dy equals. And dy would equal f prime of x dx. So you would say, well, if x changes by a little bit, then y will also change by a little bit, and the scaling factor is the derivative. So this was for one variable, how differentials were used. This dy is a differential, dx is a differential. For functions of two variables, where we're looking at a surface, you just do the exact same thing, but you say that, well, okay, at this point, if we go over in the x direction by a little bit and over in the y direction by a little bit, that'll cause z to change by a little bit. So the change in z, we'll say, well, that's approximately dz, and dz, whoa, I didn't write approximately. It's approximately dz, and dz has two components, one from the x direction, fx dx, and one from the y direction, fy dy. Let's put it into practice, otherwise it's basically impossible to read. So we'll do the exact same problem, but with differentials, to try to convince you that this makes sense. Let me put this in this box. That if x changes by dx and y changes by dy, then the change, delta z, is approximated by the differential dz, and dz is equal to this thing, fx dx plus fy dy. So here I have a function of two variables, which is just like in this box, and the x has changed by a little bit. X has changed by 0.06, and y has also changed by a little bit. Y went up by 0.08. Is that true? They both went up? Yes. So the question is, what happens to z? And we don't want to find that directly, because I don't want to square 3.06 and square 3.92 and put them in the formula. If you really needed the value of this function to great accuracy, you would do that. You just plug it into the formula. But in the real world, you might only have this information, the dx, the dy, and some partial derivatives, and you might not have a formula at all. So that's where this, why this matters. To find delta z, we say, well, I don't know what delta z is, but I know that it's approximately dz, and that's easy to calculate. It's fx dx plus fy dy. Fx is a partial derivative, and we already calculated this partial derivative. It's like x over square root of x squared plus y squared. And the y partial derivative was y over square root x squared plus y squared. I've just violated a nice rule that I've always told you, which is don't write something obnoxious if it already has a name. This is already called z. And then we can plug in all these things. So 3 and minus 4 are x and y. And z we found before was 5. So we can just drop all these things in here, and it tells us, according to the differential, how much z should change. 3/5 dx minus 4/5 dy. And you should recognize these calculations, that this was just a much faster way to get to the same thing that we calculated before. This is like, I have to do a fifth of 0.06, and that's 0.012, and here's 0.036, and then it goes down by 0.064? I don't remember. Yeah, I think that's what it was. So instead of finding the tangent plane, plugging everything into the tangent plane, solving for z, instead we kind of like skip all that stuff, and differentials let us just find how much things change. So the change is approximately this much. So here's the change we actually want. Here's the differential that we're able to calculate. It's whatever this is, 0.028 minus 0.028. Approximate the change in z. Okay, so that's this. Then, because we have a formula, we can actually find the value and figure out how far off we are. The picture you should have in your head is that there's some surface caused by this function, and we knew where a base point was, but we were trying to find where the surface would go if I moved a little bit over and a little bit toward you. Well, it might go, it'll go down by a little bit. That's what this approximation says. But we found that by like following a tangent plane and seeing where the tangent plane went. And depending on how curved the surface is, we'll be off by a little bit. So let's find how far off we actually were. So the true new value of z is square root 3.06 squared plus negative 3.92 squared. I'm still not going to get the exact value because the calculator is not going to be able to do that, but I get 4.972927. So this is the true value of the new z, which means that the true value of delta z is 0.027073. That's, when I add these together, I want it to be 5. So yeah, it's this way. When I add these together, I want it to be 5. So I do that by making this line up to be 4.9999910. So that, because like 4.9999910 is 5. Okay, so this is the true change in z, and this was my approximated change in z by just doing differentials. Didn't need any calculator or we didn't even need explicit knowledge of the function to get this. Okay, so it asked us what is the percent error. So the actual error it's the difference between 0.027 and 0.028. Which is 0.000927. And so the percent error is 0.00927 divided by the actual error, or divided by the true value. The stuff with calculators is all approximate. So I got 3.4% error. I kept a lot of significant figures throughout the way here. I only kept 2 at the end because my delta z, my dz that I calculated only had 2 significant figures. So I should only keep 2 here at the end, really. So I got 3.4% error. Yeah, so differentials allow you to approximate what happens to a surface when you move a little bit. And that's the same way that differentials did that in Calculus 1. That means that if you know partial derivatives, you can approximate changes in functions without using the actual formula of the function. That's good if the formula for the function is really complicated, or if you don't know the formula for the function because you're in like an engineering situation. That should do it. So this section was tangent planes and linear approximations. Yeah, so we got some tangent planes, we got some normal lines, and we figured out how to approximate change. Perfect. Go practice it a little bit.